Hi everyone, my name is Stephen Forrest. I'm a software architect here at MapleSoft, and I'd like to talk to you today about machine learning in Maple. I'm first going to talk a little bit about what machine learning is, how it relates to related topics such as artificial intelligence and deep learning. I'm then going to spend the bulk of my time talking about deep learning, and in particular the deep learning package in Maple. Before getting into Maple specifically, I'm going to introduce the core concepts of deep learning for those of you who may not have seen them previously, but we'll spend most of our time looking at deep learning in Maple, including some new examples of some features which are coming in the next version of Maple, but which you haven't yet seen before. And I'll finish up with some additional resources for learning and some further reading. What exactly is machine learning? You can think of machine learning as inverting the classical paradigm between the role of the program and the output in computing. So in traditional computing, you feed a program crafted by a human into a computer. You feed a bunch of data into the same computer. The program churns in the data and produces some output. Whereas machine learning, you feed in data and output. That is, data being the input and the output being what you want the function you're producing to produce given that data. You feed it into a computer, and instead of computing, it does training. And then at the end, it produces a program which you could then use in the traditional way with new data to produce new output. So machine learning, deep learning, and artificial intelligence. Machine learning is a subset of artificial intelligence. And there are many different kinds of machine learning that are currently being used. One is generally known as deep learning or neural networks. Deep learning is only one kind of machine learning and not always the best tool for the job. In Maple, beyond the deep learning package itself, which is obviously intended for deep learning, there are a number of tools which one could say touch on in some way the topic of machine learning. And these would include curve fitting, interpolation, and statistics. If you imagine a very straightforward and standard operation in Maple of for example, fitting a cubic spline to a set of input points, what you're effectively doing is providing a set of known inputs and outputs and producing a program which now can be run on a new output, that is new x values to produce new y values. And that fits entirely within the paradigm of machine learning that we just saw. So on to neural networks and deep learning. A neural network is an information processing paradigm inspired by ultimately the human brain. The idea is that you have some designated set of inputs and a designated set of outputs, and then some kind of internal nodes in between. And the key point is there's a sort of a concept of nodes and edges, and information is transmitted from the inputs through to the outputs via the layers in between. But also inspired by our brains is this notion of the fact that the information propagation is not 100%. There's some sort of notion of a threshold that you must surpass in order for information to be propagated from one node onto the other. And the way this is implemented in a neural network is via various configuration parameters and a choice of activation functions. And the activation functions are the mathematical functions that define the information propagation forwards through the network along these edges. So these neural networks may have zero or may have many internal nodes of these so-called hidden layers. And when we talk about a deep neural network, we're usually talking about one with one or more hidden layers. And this concept of a neural network has been around for for many decades, since probably the dawn of sort of the modern era of computer science, and maybe 50 years ago. But until recently, we didn't have the hardware to really much with these kinds of things, and we additionally didn't have the vast amounts of data to throw at these tools to demonstrate their efficacy. In recent years, there's been an explosion of interest in deep learning specifically, and many different software companies have each developed their own deep learning platforms. And as is often the case, there's initially many players who rush in, and then after the dust settles, there's maybe a few left standing. And I would say that the two that are sort of have got the most traction, probably not surprisingly given their benefactors, are Google TensorFlow and Torch, which is created by Facebook. So we're just going to focus on Google TensorFlow, but many of the core concepts here are shared by many, if not all, of these computing platforms. In particular, they offer tensor computing in arbitrary numbers of dimensions with strong acceleration via graphics processing units. If you want kind of a maple analogy for this kind of operation, we would be talking about numeric operations on high dimensional R tables, that is, R tables with hardware data type, and using CUDA or similar GPU-based technologies. So Google TensorFlow is available for free from the website tensorflow.org. It is Apache licensed. Its current version is 2.3.1, released just last month. And it fairly recently upgraded last year to major version 2. With that came a set of very significant API changes. So in many cases, the models written in 1.x are not automatically compatible with models written in 2.x. We'll talk a little bit more about what that means for Maple specifically, given that we are using TensorFlow as our backend. So I've briefly kind of talked about the idea of a neural network. I didn't get too much into to exactly how one trains it, but I think you get the general idea that there's a set of inputs, there's a set of internal nodes with essentially a bunch of configuration parameters, and that's where all the magic is, and some set of outputs. So there's a couple of specialized kinds of neural networks that are suited for specific tasks, and that come up a lot. These are recurrent neural networks and convolutional neural networks. Recurrent neural networks are often known by other initialisms, such as long short-term memory and GRU. And these core network types may be composed together on top of one another in arbitrary ways to build more complex models. Some examples of powerful types of models that are created by composing these types of neural networks include so-called generative adversarial networks. This is the basis of this deepfake technology where you craft one actor's head on top of another, or maybe de-age someone, as we saw recently in the film The Irishman. And another type of composite network is also these seek-to-seek models, which is sort of an advanced form of recurrent neural network, where you're mapping, instead of numbers, a finite set of numbers to a finite set of numbers, you're mapping sequences of arbitrary length to other sequences of arbitrary length. With recurrent neural networks, the core idea is that the output is not just a weighted combination of the inputs via some magic inner nodes, but in addition depends on hidden state vectors whose value is set by a previous iteration through this very network. So essentially, the network has a memory, and it remembers what it saw before on some level, and maybe not as the memory of the n minus first set of data is maybe not as important to the network as the data that it's working on at this very moment, but it still is in there somewhere. And you tend to see recurrent neural networks frequently used in applications involving text processing or classification, such as automatic language translation. Convolutional neural networks, on the other hand, are typically used in analyzing numeric data for applications such as image and video recognition. So a typical sample tasks might be image classification. So is this picture a picture of a dog or a car? So here you have a network which essentially performs some kind of aggregate operation on parts of a numeric matrix, if you like, and effectively is trying to search for higher level features. So the first level would be very low level things such as nodes, edges, or pixels, and subsequent layers would learn about higher level shapes, combinations of nodes and edges, etc. Okay, now we're on to deep learning in Maple. So the deep learning package in Maple was first introduced in Maple 2018. It's an interactive environment built on top of Google TensorFlow. The current version of Maple includes TensorFlow version 1.15, but the upcoming version of Maple will include a version of TensorFlow which is beyond the 2.x threshold. In particular, it will include significantly more parts of the TensorFlow API, including the Layers API, which will enable the use of many more types of models, including convolutional and recurrent networks. So at this point, I'd like to show you some examples of the Maple Deep Learning package in action. And I'm going to walk you through 3 different models, one of which works in Maple 2020, and the other 2 of which are a sneak preview of what's to come. Okay, so now we're going to see some examples of the deep learning package in action. We first open up Run with Deep Learning, and the first example we're going to talk about is the so-called Iris dataset. This is a classical dataset involving 3 types of flowers, and the task is from 4 physical observations about these flowers, we have to classify the species. And if we just visualize within Maple some of these, the details of these flowers, you can see that the color represents the species. So you can see that by physical characteristics alone, one of the 2 species is clearly differentiated, and the other 2 are kind of commingled. So the task is primarily to distinguish these 2. So if we just quickly segregate some training and test data, and then define some integer assignments to the types of species, so do a little data preparation here, all we really truly have to do is run this one single command of DNN classifier, which we then train. This is DNN stands for Deep Neural Network. And if we run 5,000 steps of training on this data, we can see when we pass through the result into the evaluator that we have achieved 96.7% accuracy on this data set. If we pass in a new sample point, we can estimate what it probably is based on what the neural network model suggests. And it is, in this particular case, 98.5% certain that this particular sample is the 3rd of that species. I think that's versicolor. Moving on to the second example, this is one that is based on some upcoming technology, which will be in the next version of Maple. This uses a so-called sequential model. This is based on the PIMA diabetes dataset, which is essentially is attempting to predict whether or not people will contract diabetes based on various other physical observations about them. In particular, these people are all women, so it includes various one of the details it includes is whether or not the number of previous pregnancies they've had. So we define a sequential model with 3 dense layers. I won't get into what the parameters mean, although I'll note that the middle 8 for this dense layer represents the number of independent variables going in. That is the number of columns which are being used to formulate the model. If we compile the model and then fit it, we now have something we can work with. And in fact, the result after evaluating the test data is that it's 71% accurate, which is not perhaps as good as we had seen previously, but is pretty good from a health predictive point of view. You could work with that, and you could probably use that to inform decisions, medical decisions about when you might want to observe someone and when you might test them. To get a sense of what this actually looks like on specific individuals, let's take the last 9 people from the data set and then just look at what it tells us about them. So of course, we actually know whether or not these people have diabetes or developed it later. So these are the predictions, and you can see how they line up. So in this particular case, you can estimate, I guess you can say that anything under than 50% is predicting that the person won't have diabetes, and anything over 50% will predict that they do. So we have a miss in the first row here, and then 2 hits, I would say, 3, 4, 5, 6, and then another miss, and then another hit. So that is in the sense that the model has correctly predicted whether or not this person has or hasn't developed diabetes. So that seems to accord vaguely with the 70% accuracy we calculated before, but it's always nice to compare this to actual numbers and get a sense for things. The final example I want to show you is a little bit more advanced and makes use of a convolutional neural network. So I'm just going to close this up. So this last is the so-called CFAR10 database, which is a dataset consisting of 60,000 color images in 10 classes. So if you want a quick preview of this, if you can look here, you can see that it basically consists of a number of rather low resolution images of various objects, and those objects are airplane, automobile, bird, cat. These are a number of non-overlapping categories. And here we define a model which we're going to train to recognize and categorize appropriately some subset of these images. So this is the lengthiest step of all. This is 10 epochs, each of which takes about half a minute. So because this is pre-recorded and for your benefit, I'm going to jump ahead. Okay, so we can see at the end we have produced something that reports a final accuracy of about 78%, which is not bad for a categorization of 10 things. If we evaluate this in our test data, we get an accuracy report of 68%, which is also not bad. So again, if we want to actually see what this looks like for particular images, we can grab some. We'll generate a set of predictions for the test data. Here, we fetch an image which is obviously of a bird, but the neural network has guessed that this is an automobile. Here we fetched an image of a boat, which obviously the neural network thinks is an airplane. So after omitting the final example, I am finally able to find one where the prediction actually aligns with reality, and it both predicts and is a cat. So I hope you found that foray into the deep learning package to be helpful. So I'd just like to finish up with a few resources and further reading. So there's some good overviews of TensorFlow available online, of course. There's also a free book available from MIT about deep learning, and a free YouTube course in deep learning from MIT, which you can access at introtodeeplearning.com. Also, further reading, there's a number of interesting papers on the topic of deep learning, too many to mention, of course. Some that are of particular interest to those interested in computer algebra would include some of the papers presented at the Maple Conference last year, including by Matthew England, Dorian Florescu, and as well, there was an interesting paper by some folks from Facebook earlier this year, published on Archive about deep learning for symbolic mathematics. So if you're interested in this topic, I encourage you to check out some of them. Thanks very much for your attention.